Hello, my name is John Holm, and this is my CompTIA casting call submission. Today we're going to be going over Network Plus, specifically N10-0800, exam objectives 1.4. We'll be going over binary conversion and touching base on IPv4 subnetting. Let's start with binary conversion. Some background first. An IP address is a unique identifier for a device on a network. In the context of the internet, it's like a home address for your computer. You can also think about it as your whole phone number, right? A subnet mask is used to describe or delineate the two parts of an IP address, the network portion and the host portion. The network portion could be like your street address, or the area code for your phone number. The host portion would be considered like your actual house address or the 7 digits of your specific phone number. Binary to IPv4 conversion and vice versa is simply the process of turning the 32-bit binary of that dotted decimal IPv4 address back and forth. So in this example here, I've given the dotted decimal of 192.168.1.216 correlates directly to this binary, which is highlighted and color coded for us to look at. The first 192 correlates to 11000000, 168 to the pink, and so on and so forth. Even though an IPv4 address might be represented as dotted decimal for us to read, computers usually read it as binary. So it's important for us to be able to convert back and forth from dotted decimal to binary for networking and subnetting purposes. IP addresses that are 32 bits long. This length identifies the total number of unique addresses that can be created, that are possible. Since each bit of an IP address can either be a 0 or 1, two combinations, the total number of possible combinations of those 32 bits can be calculated using the power of 2's. So 32 bits with a combination of 2 per bit, it's 2 to the power of 32. Or it can be 2 times 2 times 2 times 2, 32 times, right? We get the point. The total number of IP addresses in IPv4 comes out to 4,294,967,296. It's also important to know that even though we read from left to right, the calculation or interpretation starts from the rightmost bit because it represents the smallest unit, 2 to the power of 0 or 1 in decimal. Each bit to the left represents a higher or the next power of 2. This binary conversion key that I've put up here, this is the way I was taught, and it's honestly the easiest way to memorize and the easiest way to figure out how to do IP, dotted decimal to binary conversions in your head. If you can memorize these 8 values, which are 128, 64, 32, 16, 8, 4, 2, and 1, in order from greatest to least, you'll be able to do this conversion in your head at some point, right? Everything requires practice. So for each, like I mentioned, the IP addresses are 32 bits, and we look at them in octets or sets of 8 bits in binary. And in dotted decimal, we look at it as octets as well. But each one of those 8 bits in each octet represents one of these values, and they're usually in this order. So we're going to use an example here, 10.59.164.243. The way I was taught is, and we'll do each octet at a time, the way I was taught is we have to try to fit one of these values from moving from left to right into 10, okay? So if we move from left to right, we have to meet that value without exceeding it. So we're going to start with 128. 128 is larger than 10, so it doesn't work for us. We'll leave it as 0. 64 doesn't work. 32 doesn't work. 16 doesn't work. But 8 does. 8 works for us. That leaves us with 2, right? So we're going to put a 1 underneath the 8 because we need it. If we move forward, we have to add whatever value we want to try out. So if we try adding a 4 to 8, we get 12, which is over the value of 10. So it exceeds it, so we can't use it. So we'll leave it as a 0. We're going to move on to 2. 2 works. 8 plus 2 actually meets that value of 10 exactly. And since it meets it exactly, we don't need the last value of 1. So we're going to leave that as a 0. So that gives us a total binary value for the dotted decimal notation of 10 is 00001010, 8 bits. Okay, we're going to move on to the second octet now. 59, same process from left to right. 128 doesn't work for us. 64 doesn't work for us. 32 does. 32 works, and then if we add 16 to 32, we get 48. 48 works. If we add 8 to that, we get 56. Now, if we added 4 to 56, we get 60. It goes over 59. So we're going to skip 0. We're going to skip 4. We're going to add 2, though. That gets us to 58. And now we just need that one, the last value for an odd. And here's another rule. If the octet ends in an odd number, you always have that last bit turned on. So that gives us a total value, binary value of 00111011. For the third octet, same thing, left to right. We're going to start with 128. 128 works for us. 64 is a bit too big, doesn't work for us. We'll move on to 32. 128 plus 32 is 160. That'll work. Okay, 160 plus 16, that puts us over. 160 plus 8 puts us over, but 160 plus 4 puts us exactly where we need to be. So we're going to go ahead and put a 1 underneath the 4, and we're going to leave 2 and 1 turned off in this case. So it gives us a binary value of 10100100. And finally, for the last octet, we're going to start over here. 128 works for us. 64 works for us. 32 works for us. 16 as well. That gets us to 240. If we added 8, it'd be 248. That's too much. If we added the 4, that'd be 244. That's also too much. But 242 works. And then 243 gets us there exactly. So final binary value is 11110011. Next, we're going to move into some IPv4 subnetting. IPv4 subnetting is a technique used to divide a single IP network into multiple smaller networks called subnets. This process allows organizations to manage and allocate their limited number of IP addresses more effectively, improving network performance and security. So let's explore how IPv4 subnetting works, why it's used, and some key concepts involved. Like I mentioned, efficient IP address usage. This avoids the wastage of IP addresses by matching the size of the network to the actual number of hosts needed. Improve network performance by dividing larger networks into smaller subnets. Broadcast traffic is minimized, which reduces network congestion and improves performance as well. And finally, enhanced security. Subnetting can help isolate parts of a network, making it harder for intruders to access the entire network. Some of the basics we've already kind of gone over subnet mask, but a subnet mask is used to determine what portion of an IP address refers to the network part and what portion refers to the host part. Like the IP address, the subnet mask is also 32 bits long, and a typical subnet mask is in binary, looks like a string of ones followed by a string of zeros. The ones cover the network portion and the zeros cover the host portion. That's it for today. In the next video, we'd be going over the rest of IPv4 subnetting and also some CIDR notation, the good stuff. Thank you for watching.